Hi, everyone. Welcome to Logicworks Container and Serverless Computing webinar. Here we're hoping to help you to select the right platform for your application. My name's Phil Christensen. I'm a Senior Solutions Architect and former DevOps engineer for Logicworks. So a little bit about Logicworks. We design, build, automate, and manage AWS clouds. We work basically on every part of your cloud migration journey. And increasingly, we've been getting a lot of interest from people about two major topics, the world around containers and the world around serverless, which we think are very compatible. Just a quick note, this presentation will definitely be mailed out afterwards to anyone who has signed up. Also, at the end of this discussion, we'll have a question and answer section. So if you're using the webinar client, you can put in some questions along the way, and we'll answer as many of those as we can when we get to the end. Anyways, the standard deployment model these days for any kind of applications that you deploy on the cloud is changing very rapidly. It used to be that there was a few sort of standard practices. Increasingly, people would use CI/CD pipelines to automate the process, but the process of deploying an application was usually rather at least task intensive. Even if you automated the process, there were still many steps that had to happen throughout there. And there were many challenges that came around due to the needs of running various applications and different frameworks and architectures on the same set of computing resources. The two options that have in recent months become particularly prominent in this space are containers and what people are calling serverless. Containers, in this discussion, we're pretty much going to be discussing Docker containers, although there were a few predecessors to the Docker platform. Docker has really taken the leadership in this space, and primarily the choice that Docker users are confronted with is what kind of orchestration layer to use to manage their Docker workloads, as well as some of the new services that are coming out of the cloud providers that make it even easier to do so. For the serverless tools, many of these things were initially came to the fore, tools around essential glue around IT automation. This would be the Lambda service from AWS and the function service from Azure. There's increasing use of tools that allow you to deploy even traditional web applications through a serverless architecture. So we'll be talking about the various use cases for each of these, but our position going forward is that these are two technologies that are essential for anybody working in this space to understand, because depending on the task that you're looking at, depending on your project at hand, one or the other may be a better choice for your particular organization. Now, there is one core common aspect to both of these technologies, and oftentimes this gets referred to as things like immutable architecture, but I like to use the term reusable artifacts, because in many ways that's really the key element of both these technologies. Is we're going to establish a process, usually one that's dependent on leveraging a continuous integration or continuous delivery pipeline, and create reusable artifacts, reusable code objects that are already compiled, already ready to go, and can be easily delivered from one environment to another. Now, every artifact we create, whether it's a container or a serverless application, is going to be created by a very specific recipe or manifest. So we know that no matter who is responsible for compiling this app or installing this app, the same thing will get installed either way, because we're going to be following a very fixed set of guidelines. Also, this is getting us into that infrastructure as code mentality as well. We also want to make sure that we recognize the value of a common interface. If our operational teams, only have so much time to learn how individual applications work. So by giving them a common interface to wrap each of the applications that your organization might create, it reduces operational complexity and makes things a lot easier to get deployments ongoing, no matter how large your organization is. And as I mentioned before, throughout this process, the same artifact is run, whether you're in local development, production, or any other part of the software development lifecycle. So let's talk about containers first. Now, why would we use, what are containers all about? Why do we use them? And this is a set of graphics that I put together that I feel like gives a good handle on some of the challenges as you install more and more applications, whether you're talking about a single server, or a cluster of compute servers. The same sort of issue is at hand. You're trying to, as efficiently as possible, use the compute that's available to you, while also trying to share some of the the potential possibilities for downtime and so forth across this cluster. We're going to have, potentially a very large set of applications deployed, whether we're using microservices or other applications, and we want to make sure that we can combine those in an efficient way across our various compute units. But depending on the applications we're deploying, and depending on how much legacy apps we have to deal with, this can be increasingly difficult. If we look at the left-hand diagram here, we see a potential server that is just running a typical host OS on top of it. Now, it doesn't really matter whether this is an EC2 instance, an Azure virtual machine, or a physical server in your on-premise environment. You have the same sort of concerns. You have a number of applications or sets of software that you need to deploy, but they all have different characteristics. Many of them have different dependencies. And if we look at an example like, we have apps 1 through 3 on this left-hand diagram look relatively straightforward, but app 4, we're using this to represent a very complex application with many complex dependencies or strange requirements for deployment. And this can make adding additional applications into this environment afterwards much more difficult. So what Docker lets us do, much in the same way that conventional shipping containers give us a standard sort of packaging, a standard interface for collecting a number of large container ships, we have the same opportunity with applications in a Docker managed OS, is that each one of these applications is sort of wrapped. And behind the scenes, many people ask what's the difference between a virtual machine and a Docker container. And the fact is a Docker container is really just a set of processes on your application that have been carefully, a set of processes on your server that have been carefully wrapped together and sort of hidden from the top layer of, when you're just doing your list of processes at your host operating system. There's another sort of set of processes that are grouped together. So this doesn't have the heavyweight overhead that a whole VM does, like when you're running something like VMware or even within a given instance of using something like VirtualBox. So with this common standard, this common packaging standard, and a common interface for running, deploying, and managing workloads, it becomes easier to mix and match the different applications we might need to deploy on a given piece of compute infrastructure. Now, the first place this starts becoming really valuable to us is really in local development. The first benefit of a containerized development approach is the fact that you can now deploy the exact same artifact to your server that was created in development. It used to be oftentimes that in development, we would maybe run with less memory, less CPU, and some of those items. But one of the things that was often the case is we usually had to compile our application, whether this was compiling static assets or taking a series of different dependencies and installing them all at the same place. We usually had to recognize that that process was going to have to be completed and repeated each time we move the software to a new server or to a new environment. By using containers, we build the containers ahead of time, oftentimes on the development workstation, although this can just as easily happen on a continuous integration server of some kind. And we have the opportunity to run that same exact bundle of code, regardless of whether we're in production or in development. We can, as I mentioned, we can use reduced memory or CPU footprint where appropriate, but we can also use different technologies to deploy multiple copies of these applications, knowing that each installed copy of that app is identical. Now, if we take this to the next logical conclusion, we see that container portability is really an inherent benefit and goal of the Docker runtime. We basically want to be able to take any given application and deploy it anywhere we need it to run, whether it's in a QA environment that maybe is under constant change, a staging environment that maybe isn't used all that often, but is only used when you're doing really complex deployment changes, or a true production environment. We're going to be running that same set of assets, and the only thing we're going to do is change some of the configuration variables and so forth that are presented to these Docker containers as environment variables, mounted volumes, and memory and CPU limitations. Now, there's a number of additional benefits that we get from this. We have a container image, first of all, that behaves exactly the same no matter what host we're running on. But we also can do some things to, for example, we can encapsulate older applications. If we have, for example, an application that requires an ancient version of CentOS, maybe you have to actually use CentOS 5 and you haven't had a chance to actually upgrade it to a proper version. This is sometimes a reality of the industries we work in. But now we have an opportunity with Docker to run a tiny little Docker container running that CentOS 5 distribution and having our legacy application run on that while still being deployed on a contemporary, highly available environment with some of our preferred operating system choices, entirely up to date. The other thing we can do is if we have, again, that example from the first slides, the very complex dependencies or very complex compilation strategies. Sometimes different library dependencies can be really tricky to install, particularly with compiled C applications. By leveraging Docker, we can sort of keep these things nicely sort of bound together and pre-compiled and still shift them easily between each development environment that they need to be a part of. Now, one of the things that's inherent to using containers is something that's called container orchestration. And what this really comes down to is that to get the best benefits out of the Docker containers in your architecture, you need some software to be responsible for moving the containers around to respond to things like auto-scaling events, changes in availability, if there's a failure of an application node, or if there's a failure of the backing host that actually runs that container. We want to make sure that any of those running containers on that instance are properly moved to other available hosts. We want to make sure that as we have needs for high availability, that we can ensure a certain number of these containers are running at any time. And the key to doing that is orchestration. So we're going to talk about three major orchestration tools right now. And this is a very active community. And really, although we're trying to outline some of the benefits and considerations of each of these tools is a very useful use case for particular services. And we're going to go through that at the end as far as how these things can be best used and where you get the best benefits. But first, we'll talk about Docker Swarm. It's oftentimes very high on people's list of things to investigate because it's got that Docker name brand recognition. It does ship directly with Docker. So if you've installed Docker on any of your servers, you also have the necessary tools installed to run Docker Swarm. It has one of the simplest configurations of any of the orchestration tools, but it does have some limitations and some things that you should keep in mind if you're thinking to leverage it. First of all, it has somewhat limited cloud integration. It does integrate with the things like AWS load balancers and other load balancing tools, and it has some limited service discovery capabilities, but at the end of the day, it is not particularly aware of a cloud environment that it's running in. So I would say that Docker Swarm tends to be particularly useful for people who are trying to get comfortable with an orchestrated environment or who need to adhere to a simple deployment technique, but also have more than just one cloud environment or one particular platform to run this on. But again, Docker Swarm is one of those things that anybody who has Docker has a copy of this, and it's something that's worth considering as a orchestration option. Now, Kubernetes. This is kind of the elephant in the room in a lot of ways. Kubernetes is a evolution of some software created by Google called the Borg. And this was sort of the way that Google handled deploying all of their containers for a long time. And then so when it came time to take the Borg and turn it into a community project that could be, distributed to various platforms and orchestration levels and so forth, it was turned into Kubernetes. A little fun fact is that Kubernetes is, oh shoot, I'm going to forget. Kubernetes, I believe, is a Dutch word for helmsman. And so you're going to get into this all throughout the Docker space, all these references to sailing. You're going to see this coming up again and again. At any rate, Kubernetes itself is probably the most feature-filled orchestration layer. It has an extremely large community supporting it, but across many different platforms, whether it's on OpenStack, AWS, Azure. It has extremely powerful built-in container discovery, and this really comes into play for many of the different ways that it works. Kubernetes is a great way to handle a very large amount of undifferentiated compute. It's good in the data center, and it also is increasingly very useful in the AWS cloud, especially for some of its support for the native AWS cloud services. So if you do a particular Kubernetes deployment, it'll be aware of some of the resources it needs to stand up for you. Also, we look forward to the release of the Elastic Kubernetes service, which will take some of the more challenging parts of managing a Kubernetes cluster and will be taken care of by AWS rather than us having to manage those things. But to that end, that should really cover some of the things that are my biggest considerations when thinking about Kubernetes right now, is that it does have a fairly complex install and configuration process, and it can be somewhat difficult to stay up to date because it's constantly coming out with new revisions of the Kubernetes software. The third option we're going to be talking about, and in many ways sort of my favorite orchestration layer, is the Amazon Elastic Container Service. Currently right now, we're talking about this separate from the Elastic Kubernetes service that is going to be part of this as soon as it comes out of preview. But what we're looking at here is a very much Amazon native orchestration option. And one of the things that I actually like about it is that ECS tends to focus on just the things that you really need to have a container deployment. And it's, I feel, is sort of mindful of the fact that we're running in an AWS environment where there are endless other services that are suitable replacements for some of the discovery options and so forth that are available in Kubernetes. Additionally, because of the fact of an entirely AWS managed scheduler tier or management tier, we can really be a lot more confident about the overall reliability of the platform without having to have, in the case of Kubernetes at this point, I would recommend having some kind of Kubernetes expert on hand, or perhaps some kind of managed service provider who can help you with Kubernetes. But there are some shortcomings by some people's consideration in ECS, particularly around these things that they might expect to be there because of familiarity with Kubernetes. However, we find that it is particularly scalable and robust. And at the end of the day, ECS is probably my most commonly recommended orchestration layer for people on the AWS cloud. We'll see if that changes with the advent of the Elastic Kubernetes service, but I have a feeling that both these services are going to have their own use case for some time to come. Now, each of these platforms have different characteristics when it comes to achieving high availability, dealing with capacity planning, and dealing with the deployment process. So when we're talking about Docker, we have some limitations around the management tier. We have a 3 to 5 node manager tier. And this is something you'll see not just in this presentation, but in a lot of a lot of Docker orchestration platforms that need to have a 3 to 5 node master tier. And this is because many of these leverage a quorum technology to ensure that they can keep communication with the other nodes in a high availability deployment. And very much core to the work that Logicworks does on the AWS cloud, we're always focused on high availability and planning for failure. And this is really true on any cloud. And so to that end, these are sort of the two sort of takeaways for Docker Swarm and Kubernetes, is that the responsibility for managing that tier of control plane is really a requirement, and it's something that you need to be comfortable with, because you need to go through the various steps that people have to be comfortable with to recover a management tier from failure. Now, in the case of a Docker Swarm, a failure means something like losing a particular node in that. And in that case, it'll maintain your services that are deployed, and those will continue working. But anytime you wanted to make changes to those services, you would have to redeploy that cluster. Anytime you lose a quorum in one of these scenarios, you actually are going to lose any of the data that describes how your containers are actually deployed. This is also an issue for Kubernetes. You have an etcd container or application that's running on your master node, and you have to always have a quorum of those running at any time. Now, of course, with the advent of things like availability zones and the appropriate automation, this can be done very effectively in a AWS or other cloud environment, but it's a whole level of work that needs to be done that you don't need to handle when you're dealing with ECS, which has an entirely managed control plane. There's some differences around updates and so forth, in the sense that both Docker Swarm and ECS are both fairly capable of being updated in place. While technically it is true that you can do an in-place update with Kubernetes using the KOps program, in practice this doesn't seem to work as reliably as we hope it will. And so for now, I generally recommend doing a simultaneous build of a new cluster and then migrating over to it, which can be a fairly labor-intensive process. There are some third-party distributions of Kubernetes like Tectonic and OpenShift that can do these things for you, but again, your mileage may vary depending on the application. And of course, as I mentioned, ECS is able to do its agent upgrades in place. An interesting detail about ECS is that all of the communication between your ECS worker nodes and the AWS control plane is handled by containerized applications themselves. So an ECS node is merely a Docker node that has the ECS agent installed on it. Now, when we talk about cluster capacity, I almost hesitated to include this slide because one of the things that I think is really important is that you should never really be making a decision about your orchestration tier solely based on capacity. Because if you look at some of these numbers, especially at the bottom of this graph under node support and container limit, I mean, these are real numbers that have been created by these teams as far as how much you can expect to reasonably deploy. But they all have different characteristics that can make them either run better or worse with increasing or decreasing number of containers. You know, an essential part of Kubernetes is that although it may support up to 300,000 containers, it also will often create a number of sort of helper containers to do things like hold addresses and ports open and things of that nature. So it's really just important to not really make any decisions based on full capacity, but this really is most a way to think about how you want to architect your actual clusters. In the case of Docker Swarm, I would say that it's really, because of its limitation of one ELB per cluster, I would say it's particularly well suited to be creating multiple clusters per software development lifecycle. So basically, for each application, you would have a dedicated cluster. For Kubernetes, I think that you can really get away with a single large cluster that contains all of your software development lifecycle phases, or at least break it down into maybe a non-production and a production version. But when it comes to actually using load balancing and some of the organizational tools that are built into these, I think Kubernetes has a real edge in the sense that it supports namespaces. So namespaces are a way that Kubernetes can both organize your containers into different groups, whether it's by, you know, dev, QA, staging and production, or maybe because you actually want to grant rights to individual people to manage certain applications. This is one of the key elements that Kubernetes differs from its partners in, is in the use of namespaces to delegate access to these containers. As far as load balancing in general is concerned, though, I would say that ECS probably has some of the best in breed integration between container autoscaling, ELBs, and it is also one of the few that supports ALBs, the application load balancers, natively at this point. This is in development for Kubernetes and is probably not far behind for Docker Swarm, but it's something to keep in mind if you're thinking about a project that is going to start development immediately. Now, the last thing I want to touch on is how deployments work on these different orchestration tools, because it really is arguably one of the more important parts of interacting with a containerized environment is improving the speed of your ability to deploy software. And so I would say that Docker Swarm, it's particularly nice in the sense that it's very simple and it leverages the Docker Compose standard, a very popular tool for local development, to actually specify your cluster configuration. So you have the opportunity of not only sharing your containers between your local development and any of your actual clustered environments, but you also have the ability to share your Docker Compose file between those things, which can provide some additional efficiencies. And it also has pretty effective support for rolling updates. In fact, this is an ongoing thing you'll see in all of these orchestration tools, is that deployments inherently are rolling updates that will usually deploy a container, wait for it to launch completely before it removes the old container. When we get to Kubernetes, I would say you have the largest number of deployment options for Kubernetes, and a lot of this has to do with the native deployment type that exists as an object type in the Kubernetes infrastructure. Basically, a given deployment allows you to actually describe the ongoing updates that you'll do, as well as include the items like particular secrets, storage that you may need attached to any given deployment, and other sort of concerns that are really tricky in some of the other container environments, especially if you want to use a purely containerized environment. Now, I sometimes debate the value of a purely containerized environment in the sense that if I'm going to run a Postgres server, I know that I can run it on containers. And on Kubernetes, perhaps in a on-prem environment, there might be some reasons to do that. But I really feel that if you're running in an AWS or other cloud environment, you're better off making use of some of the managed services that you have that you can use in conjunction with a containerized platform for your own custom software. So many of the applications that we write and the way we encourage people to write them, we'll use Docker for any of the sort of any of the custom applications that are written, any of the essential tools that are part of the actual application itself. And then for tools like Memcache, Redis, any relational databases, DynamoDB for NoSQL, I would prefer to use those services in conjunction with a containerized approach. The last thing to remember, though, about Kubernetes deployments, and another thing that really makes it nice if you're trying to grant a number of people access to a pool of undifferentiated compute resources, is that Kubernetes can also create the load balancers and security groups that you need when you launch a new application. So it's actually possible to have a very controlled approach and a very controlled method of allowing your users to deploy to Kubernetes while still taking advantage of all those AWS resources that it will take care of cleaning up and managing access to. But finally, I think for ECS, although the ECS service itself doesn't attempt to try to define deployments in the same way Kubernetes does, it doesn't really have to because it has such a deep integration with other AWS services like code build, the Elastic Container Repository, and it can be trivially invoked by things by the AWS API, and even Docker Compose manifests itself. But one of the biggest reasons I like it currently is because of the best-in-breed support for ALB target groups. Through this process, you could really use a single ALB to manage a very, very large microsite or microservices architecture. Again, because of the advantages of working in an AWS ecosystem, I feel like really it focuses on the things that it does well for containers and allows you to use the rest of the AWS ecosystem for the things that are better for that. Now, just to give you a quick overview, this is an example container pipeline, and although I've selected some specific vendors and these icons along here, it's worth taking a note that any of these steps can really be very easily replaced with some other common tools that are popular in many organizations' IT departments. So obviously the first step is always to have some sort of version control. If you can use GitHub if you're an Octocat fan like I am, but there's also obviously the AWS code commit tool. Internally at Logicworks, we use the GitLab service. There's also tools like Bitbucket. Really anything that is going to do version control tends to have the abilities that you need to tie it into the next step of your pipeline, which usually happens via some kind of webhook. You push a commit, and then a webhook triggers, and then some other process is your build server. Now, again, coming from the open source world, I'm quite fond of Travis CI, but increasingly in my job at Logicworks, I've been using AWS Code Build. And Code Build allows me to define both simple scripts and more complex Lambda functions to compile assets, run tests, and to build my containers. I then have to store my container images somewhere. And for most people, I recommend using the AWS Elastic Container Repository. If you're on AWS, it's pretty much your best option, as both Kubernetes and ECS natively know how to authenticate against that repository using IAM rules. And then when you leverage it in that manner, you can have a CloudWatch event that triggers a Lambda function anytime you push to that particular repository, which means that your deployment, and of course in this case I'm talking about Kubernetes, but it could just as easily be an ECS cluster or a Docker Compose cluster if you have the ability to get onto one of those management nodes. And we can use Lambda to invoke either the Kubernetes or the AWS API to publish a new deployment. and allow for a seamless update to the software that we're running. So again, your commit step, you've got GitHub, GitLab, Bitbucket, Atlassian Stash. All these are great options for your build server. For your source code control. For your build server, you can use Travis, Bamboo, GitLab CI has been a popular one for Logicworks. Jenkins, of course, the old standby. When it comes to shipping images, you can use ECR, but obviously Docker Hub is still in the running. You could also ship to an in-house Artifactory server or other binary repositories. And then finally, of course, there are any number of orchestration tools that you can leverage to deploy your containers themselves. So that's containers. But then what happens when we start talking about serverless? And the fact is that serverless is a little bit harder to define in a lot of ways, although obviously its name reflects what our goals are here. But the big element that we're looking at for serverless is primarily the use of AWS Lambda functions, or if we're on Azure, the function service that Azure provides. So what we're really doing is we're saying that we're going to exchange flexibility for scale. Because when we write to a serverless API, whether we use Amazon's SAM Local Toolkit, the serverless.com toolkit, which is really excellent, that's a favorite of ours, or some of the tools that are increasingly going to be made available as this becomes a more prominent and popular way to deploy software, we're basically saying that we're going to leverage the existing frameworks that are made available to us, and that has a few different requirements in how we do it. So for example, for an AWS serverless deployment, oftentimes we start with a Lambda function, but deploying that Lambda function is usually a matter of taking a set of code and dropping it in S3 and telling Lambda where that code is. But then more than that, we have a number of events that we need to send to those Lambda functions to trigger them to execute. And the creation of the API gateway and related services on other platforms allow us to say, all right, well, let's define a REST API that will then invoke this function in a certain manner. And then if we go as far as using something like DynamoDB, we can create extremely complex applications, both front-facing and back-office-facing, using entirely Lambda functions and a few other tools to sort of link the bits together. So why serverless? Well, some of the benefits are actually very similar to what we deal with ECS. We've got very quick startup times. We have a shared compute pool, and this is one of the minor points that differs from ECS. We can basically, with ECS, we can leverage our compute pool that we define. Also, increasingly, with the advent of AWS Fargate, we have the option of allowing AWS to allocate that pool of resources for us. But in the case of serverless, we don't even have a sort of a separation between different clusters. It's an entirely undifferentiated pool. And there's no need for orchestration because AWS or the cloud provider is going to handle it for us. We only pay for what we use, but this is taking that premise even further in that any of those times when our server is idle, we're not paying anything. And then because of that, we have the ability to deploy an arbitrary number of whether development instances or software development lifecycle environments at little or no cost. Because if our development environments are only used by a team of 5 to 10 people, we're going to see substantially less charges on that than we do on our production site. Now, of course, there are some considerations you have to keep in mind. You have a little bit less flexibility around development techniques, particularly around things like very long-running tasks. All of the function services that exist right now have to have a governor that ensures that you don't exceed a certain amount of runtime, a certain amount of CPU or memory usage, because that's the way to make a shared computing resource really work. But if we adhere to those things, we can leverage other asynchronous development techniques to make this truly successful. So this does mean that we're limited to some of the supported frameworks. Unfortunately, Ruby fans, there's no support right now, although I have seen people do some crazy things like run JRuby inside a Java runtime. So you do have a lot of different options, and you've got some reduced access to native functionality. So if you have like a Python module that needs to have a particular C extension installed, you may or may not be able to compile that for Lambda, depending on the particular library in case. The backing instances for Lambda have a wide variety of the common libraries pre-installed, but this is something to keep in mind that in some cases a pure Python, pure Java solution may be necessary. And as I mentioned, there are some limits on function execution time. But the first thing I want to talk about is the cost effectiveness of serverless, because on the surface, it can seem a little bit unintuitive. If you look at the per second amount, just sort of arbitrarily, without thinking about how you're actually going to use it, it could seem like it might potentially run up and get expensive. Or if you get a real big peak of service, what that's going to be like. Well, the reality is that if you actually sit down and do the math, you'll find that Lambda and serverless computing in general tends to be cost effective really quite far up the stack, at least until you get to fairly medium to medium heavy workloads. So it's based on the premise that, and I think some of my cohorts in the enterprise space and so forth probably see this the most. If you have a web scale application that's dealing with millions of hits a day, that may not be the case, but a typical production server can be idle sometimes up to 80% of the time. This is not an uncommon thing for us to see, even in a properly sized environment. Sometimes it's because they want to be prepared for certain peaks and so forth. It may be because they have a lot of development instances. Traditional development instances would either need to be parked or spun down or deleted when not in use to really be cost effective. But the thing is that for big workloads, there's actually a break-even point where unless you're going to have a certain throughput, a certain guaranteed number of requests per second, it's going to be more efficient for you to run your application in a serverless mold than it is on an M3 or an M4 large instance. Now, this table here was provided by an article by Andy Warzon, a blog post at trek10.com. You'll be able to click through to it when we send these decks out after the presentation. But you can see how, depending on how much memory you use and how long your function runs, you can really become very competitive with the cost of running these services on a traditional EC2 instance. So really the most important thing to do is focus on the memory and the execution time that a typical transaction in your app is going to need, because that transaction pretty much correlates to a single Lambda function in your application. Now, one of the things that comes up is, as I've mentioned, there is a limited runtime that's just simply a fact of life when you're using a shared tenancy environment like this. And so one of the things we have to know is that, like, for example, with Lambda, we're limited to a 5-minute runtime. Now, that used to be much less, and it will continue to become, you'll have longer and longer times that you can potentially run as the Lambda technology matures. But there's still always going to be an upper limit of the amount of time or the amount of memory that a given process is really allowed to use. So we can leverage technology like AWS step functions to take a series of serverless steps, a series of Lambda functions, and essentially orchestrate them. This is essentially orchestration for Lambda functions. And so what this is going to do is make sure that a particular state machine sends a certain number of arguments or parameters to the beginning of your pipeline, and it will follow that chain of Lambda functions and continue to modify that state until you get to the end of your function and your task is complete. Now, this can be challenging. It takes some time to sort of rearrange your thinking to really effectively use a sort of asynchronous workflow style development. However, what you see here is actually a real graphic that I took of a really common requirement that we have to do at Logicworks, which is do ongoing backups and ongoing snapshots of our customer environments. And one of the challenges around that is we have hundreds of customers, and within their account they may have thousands of snapshots that need to be made, AMIs that maybe need to be shipped to another region or maybe copied to another account. And increasingly, we didn't have enough time in our normal iterative script to actually run all those things in a single day. So we started leveraging Lambda functions so that we can sort of let individual client backup runs, run in one of these state machines, and then we just send it off to do its thing while we make sure that we just, trigger the scheduling of running these applications. So just sort of bring this back a little bit, we use step functions to create complex workflows around our Lambda functions, largely so we can get out of the way of the limitation of the 5-minute execution time, but also so that we can have much larger pipelines with bigger lists of objects that it's working on and use memory and CPU much more effectively. Now, what are some good use cases for serverless? I mean, the fact is that every day I find a new way, particularly to leverage Lambda in the AWS environment. As you know, a cloud engineer, I use Lambda almost more than I used to use SNS topics. For the longest time on AWS, we would always use SNS to send communications from one place to another. But at a certain point, you'd have to have something reading a queue and responding to those messages, and usually that meant an EC2 instance or something to that effect. Now, our SNS topics can directly invoke a Lambda function, and we can do a lot of different things. So we can use this for periodic workloads or light to medium workloads, as I mentioned. It's dramatically less expensive than standing up an instance, and it really takes a great deal of compute volume before Lambda approaches the cost of your EC2 instances. And the total cost of ownership is greatly reduced because you have little or no need to actually manage the infrastructure. It's also particularly good for, I wrote API-only applications, but increasingly with some of the tools available, such as the Zappa toolkit for integrating with Django and some of the other toolkits that are out there, you have the opportunity to do any kind of web-facing application by really taking a series of Lambda functions and integrating them with the API gateway service. Keep in mind that a REST API is really no different than a web page. So if the web page happens to return HTML, that's fine too. It's also useful for really long-running or deeply integrated AWS scripts or applications. Because of the way that every Lambda function has an execution role, and because of the opportunities around asynchronous execution and the step functions, you have the opportunity to run very complex workflows. Again, this is particularly useful if you have a large number of objects that need to be processed, if you have a large number of network connections that need to be made that can take an arbitrary amount of time. This is a great way to parallelize your application and get a much better efficiencies. So I wanted to go through some of a sort of quick summary of some of the #1 use cases for each of these tools. And of course, this is really just sort of my opinion with some feedback from some of the serverless people at AWS. But what we're really looking at is that for each one of these tools, you may find that it's particularly useful for particular situations. Docker and Docker Swarm particularly is really the lowest common denominator. This is something that you can run on basically any sort of compute instance in any sort of cloud environment with just a limited amount of internal networking. It's able to have a very robust, high availability Docker container deployment. It is, however, the lowest common denominator. So there's many features that are not necessarily available for it that an advanced user may find they miss. Serverless is particularly useful for autonomous IT, or any time that you have event-driven actions that you want to be able to scale to arbitrary amounts. Like again, as a managed service provider, the biggest thing that comes up for us is the need to run all these different scanners and detection tools and so forth across all of our various clients in a way that is scalable across hundreds or thousands of accounts and thousands or tens of thousands of instances. Serverless also probably has some of the most efficient scaling practices. Now, it's important not to take any of these things, too extremely, but when it comes to scaling ECS, ECS can get pretty high itself, but you're still at a certain level going to be organizing your applications into clusters. Although Fargate certainly will make that a lot easier, you're always going to sort of get a little bit slightly more efficiencies out of serverless because behind the scenes it's going to be entirely managed by AWS. And AWS has got the actual incentive to make sure that that scales as efficiently as possible and that it can move across application, server, and other boundary lines. Now, as I mentioned, ECS still has exceptional scale. And when I say conventional software, I mean if you're running your typical application software that runs some kind of event loop, that runs infinitely, that it's running all the time, and that is packaged using sort of the standard best practices that we use these days, you'll find that ECS is a great fit for people in the AWS platform who want to start taking advantage of container orchestration. Kubernetes, when you select Kubernetes, you're essentially exchanging simplicity for flexibility. Now, the advent of the Elastic Kubernetes service really is very exciting, and I think that's going to bring Kubernetes to a whole new set of users that were not able to leverage it before. But even with a fully managed like application tier, management tier, you're still dealing with a much more complex application. There's a lot more moving parts involved. The capabilities are far more extensive, but it takes some time to learn. There's a bit of a learning curve there. But the other thing that Kubernetes particularly excels at is being a standard management layer for undifferentiated compute. This word comes up a lot in my presentation, but basically, if you have a great deal of compute resources that you need to provide access to, and this, in many ways, is often a problem for an on-prem environment. Kubernetes can be a great way to provide controlled access to a set of compute resources because of the flexibility and power it has around namespaces, deployments, and other more advanced object types. But I've come to the end of my presentation here, so we're going to go through some of the questions that people have submitted here. But just a quick reminder that Logicworks is there to help you and your team train your staff, get expert advice, build new environments, or manage existing environments. So if you have any questions about cloud management, cloud development, or any of the things we've talked to today about containers and serverless, please feel free to drop us a line. All right, let's see here. All right. Well, the first question I think was about just making sure we share the PowerPoint presentation. So that's no problem. And so someone's looking for a little more elaborate discussion on how we actually push containers, and some of the best practice around pushing containers in AWS. And so I'm going to just pop right back to a couple slides ago. And this was really I'm really pleased with the slide in a lot of ways because these are some of my favorite tools, but also at the same time, it sort of shows the various options that you have around doing container deployments. And so the first thing that I generally recommend with regards to Docker deployment is that you start being comfortable with creating Docker files. Now, there's many different ways to create a Docker image, a redeployable artifact for Docker, but the sort of best practice is going to be to leverage that infrastructure as code mentality and create a Docker file that gives those exact instructions on how to create the container. So then once you've done that, you're going to need a way to iteratively compile that application. So that's where we get our build chain and so forth. And then I think that when it comes to deployment, really one of the easiest ways to make sure you achieve this across the board is always going to be with a very consistent build pipeline. So like I said, whether you use the Travis CI service or some other kind of service like code build, it's definitely going to be in your best interest to automate the creation of your containers and automate the pushing of your containers into some kind of hosted repository. Now, I really recommend ECR for a lot of reasons, as I mentioned. It's also nice that it has some technology that allows you to automatically age out old containers that you've pushed previously that are no longer used. And then, of course, it provides the ability to trigger Lambda functions on push. So if we want to make sure that any new containers pushed with a certain tag automatically get deployed to a certain environment, this is how we do it. So it's really a lot about following some of those standard best practices that we get around CI/CD to ensure that you have a pipeline that is able to go from 0 to 60, even if you're caching these elements along the way, because we always want to be able to recreate our Docker container from nothing. And we want to make sure as much as possible that we have the ability to do continuous pushes so that we can push on new versions anytime we want. One of the next questions I'd heard was what the difference is between Swarm and Docker Enterprise Edition. This is actually a very good question and not one that I think I can really effectively answer right now. My assumption would probably be that it's based around two major things. Right now, the Docker Swarm, the open source community edition, doesn't have a very advanced web interface. It's rather simplistic. And it also isn't particularly, it's open source, so you don't really get any sort of support with it. So I would assume that with Docker Enterprise, you're going to be eligible for actual, phone support on some level, as well as the fact that you'll probably have some sort of more robust web interface to manage and monitor your cluster. That is one of the things that there are some shortcomings with Swarm about monitoring tools. Kubernetes, obviously, or perhaps not obviously, Kubernetes comes with the Prometheus monitoring tool in play, and of course ECS has CloudWatch and sends a number of metrics via CloudWatch. So basically I would say that if you're looking at running Docker on physical infrastructure, you might want to look at Docker Enterprise, but also too, as this space expands, I wouldn't be surprised to see Docker Enterprise as a licensed hosted solution for AWS. It'll be interesting to see how they fare as the Elastic Container Service comes to the fore. I have a question about using containers and still achieving PCI and HIPAA compliance. This is a good question because actually it kind of depends on the particular orchestration tier you use and how you install it. Now, both Swarm and ECS by default will automatically use HTTPS to protect all of the API communication. However, Kubernetes, that's an additional thing you have to configure. Now, many of the commercial distributions of Kubernetes will also cover that and do SSL for you, but depending on the way you stand it up, that can be something that needs to be dealt with. So it's always worth ensuring that you have some sort of professional or someone who's got a lot of audit experience to sort of go through your architecture and ensure that you haven't opened up any sort of compliance flaws. Nothing about Docker or containers or serverless is inherently incompatible with PCI or HIPAA, but it's always something to look out for. I have another question of what's the impact on all these tools on developers? The question is whether they develop differently or if this is all transparent to them. And I would say that this is sort of that sea change moment where the promise of DevOps has always been that developers will have more ability to interact with the ops side of a software process, that that they could have basically the ability to fix issues that arise in production without needing direct access to it, that they could create artifacts that their ops team would be able to easily deploy on their own. But then there's also things like with serverless, it may get to the point where there's no reason for anyone else to do it, since the developer can just as easily deploy the application themselves as to use some sort of process. So I would say that in general, developers pretty much find that they like this because you get, first of all, an environment that much more closely matches production. If you use, there is obviously a lot of different tools, but if you become comfortable with what each of these tools do, it can make debugging and managing your app a lot easier, particularly if you develop for Docker. Definitely look into Docker Compose. It's one of the easiest way to run a number of containers for you all at the same time while interspersing their log messages, so you can actually see if you've got a complex microservice-based application, you can see where the failure actually happens. So there's some questions around service discovery functionality comparisons between these different tools. So service discovery is starting to mean some different things to different people. One of the first challenges is that the logic is thus: is if you deploy a whole bunch of containers into your cluster, you ought to be able to detect where any of those containers are via various metadata or other lookup functions. So in the case of Docker Swarm, whenever you create a service, and all these tools describe a service as a sort of like a promise that a given container will be kept running and will run a certain number of containers at a time. In Docker Swarm, anytime you create a service, it's going to get a dedicated internal DNS name. So if another application needs to route to that service, you just would, in some fashion, code in the DNS name internally. That DNS name will stay the same even as the containers rotate in and out. For Kubernetes, it's actually got a really robust discovery system based on what it calls, there's really a couple different things. There's annotations and labels. And labels are the primary way that you would look up an arbitrary container, but this is also a key element to how replication works on Kubernetes. When you have a container that you want to run multiple copies of, the way that works is by creating a replication configuration that basically says, look up this container and by tag and deploy it X number of times. So I would say that Kubernetes really has the lead over Docker Swarm, but then ECS, because of the integration with Route 53 and the internal Route 53 technology, and ECS's own support for automatically updating target groups and load balancers, I would say that while ECS's discovery isn't quite as robust as Kubernetes, it makes up for it, again, by having that AWS ecosystem to work out of. So there's some question about how the Azure Kubernetes service compares to ECS and OpenShift. And I would say that so far what I've seen from the Azure Kubernetes service is that it gives you all the tools to set up a running cluster, and it definitely has, it does what's advertised, but at the same time, it doesn't, we're not dealing with a managed master tier. And so far, I don't know. So far, I'm kind of hesitant to really go for that because some of our Azure clients so far aren't necessarily our strongest Kubernetes clients. So at this time, we're sort of a mix of Azure and AWS for Kubernetes. And I'd say that there's probably no major reason to use either right now. But as soon as the AWS Elastic Container Service is released, I think that they'll have the edge, at least until Azure turns around and probably does the same thing. But yeah, definitely both are candidates and are both worth looking into. So are there any differentiators with respect to being able to monitor container performance? I would make the case that none of these things, as far as monitoring performance, you're probably going to get the best results out of ECS or Kubernetes. But with Kubernetes, you're going to have to set up the Prometheus monitoring and make sure that those events are being sent somewhere that you can do something with. Whereas, setting up CloudWatch notifications is really easy as far as just you put in an email address and you can get a notice right there. But I would say that performance itself is largely the same across all these because at the end of the day, a container is just a set of processes running with a little bit of syntactic sugar to sort of keep them connected together. Another question about the slides, just a reminder that we'll be sending those out to everybody who signed up. So far with serverless, we've been talking a lot about AWS, but depending on the serverless framework you leverage, you can just as easily do these same things on Azure in their virtual cloud. So basically this would be a scenario where you'd use a set of tools, similar tools on AWS with similar limitations around runtime and so forth, and a similar requirement that you stick with particular supported application environments. So as far as security, I would say that these things are, I would be more comfortable running a serverless component on Lambda or what have you, than running a EC2 instance or a VM with an actual set of, my own installed software on it. I always sort of hedge on the bets that I'd rather have somebody manage my infrastructure than have to do it myself. I want to focus on the things that are different for my workload, not the things that just anybody can do. So I would say security-wise, you know, I find Lambda to be a little more secure, but of course, nothing's inherently secure. So there was one last question. It's a really interesting one about securely delivering Docker images. One of the things that's really nice is that every image you send has a checksum associated with it. In fact, the checksum process is actually used when you're compiling or building an app over and over to save some time on those interstitial steps, because it basically checksums. It makes a new image for every step in your Docker file creation, and each one of those images it has a checksum associated with it. So when it goes and it runs that process again, it can see whether it already has what it calls the interstitial image for that step. And if it does, it just goes right on to that next instruction. So basically, key to Docker images is the fact that everyone has an associated MD5 checksum, which is seen all over the Docker ecosystem. It is worth considering signing Docker images because although it's fairly unlikely, it's not impossible to make a MD5 checksum collision. So if you really just want to add an extra level of security, you could do so. But if you're using a private container repository like ECR, and you know that only approved users have access to that repository, you can get a lot of security just by using a private repo as opposed to Docker Hub. But yeah, if you want to take that extra level, you could definitely add image signing. And then there's just one last question about using container services to run A/B testing. And this is an interesting one, but again, there's really nothing inherent to containers that would prevent you to do it. In fact, it probably makes it quite a bit easier because anytime you push a container, you can associate a tag with it, whether that tag is a version string, a checksum from your Git repository, or anything of that nature. Every container you push has some kind of unique identifier. So to that end, it wouldn't be that hard for you to, say, create 2 different target groups on, or what would I do actually? Maybe create 2 different endpoints and then use like a Route 53 failover or weighted domain. It's an interesting question. I would say that there's nothing inherently built into container services that makes A/B testing automatically available, but it's a lot easier to deploy multiple versions of this because of all those steps that we've discussed. So I think that was it as far as questions. I want to thank everybody. Oh, there is one last really good question, just because I haven't touched on this at all, but this is the last one I'll take. There was a question about running Windows-based applications, and it is true that right now, containers are largely limited. Docker containers are largely limited to running Linux workloads. However, Docker for Windows does now support using, I think it's the Windows Server 2016 core to actually deploy applications on that. So you'd have to use Windows instances to run the containers, and then the containers themselves, you don't have the same freedom of distribution that you would have on a Linux environment. But then you still have the opportunity of isolating these applications, making them easier to move around. And I know that ECS definitely currently supports Windows containers. It's still in beta, but it's supported. For the other platforms, I actually don't know. I would guess that probably Docker Swarm is probably closest to having support for Windows, and I really don't know about Kubernetes. It's a really good question. I'm gonna have to look into. But anyways, that's the end of my presentation. I want to thank everybody for coming out. Again, we'll be sending a copy of the deck to everybody who signed up. Also, if you have any sort of questions, feel free to reach out to Logicworks. We're available to just talk all out about containers, or to give you a more robust overview of whatever your cloud workload might be. But thanks again for joining the webinar, and have a great day.